So let's jump out of an airplane and see what happens with this model. And terminal velocity, again, is g over k. Initial velocity is 0, and we're jumping from 10,000 feet. So now I looked up terminal velocity, and it's, Wikipedia says it's 122 miles per hour. That's pretty close to 180, so I just rounded up to 180, and to keep the numbers a little simpler. So 180 feet per second, that is. So terminal velocity is 180 feet per second. And I have to call it a negative because it is falling down, and down is negative direction. So I need that negative there. And that negative's, you can't ignore those negatives. I did, when I shot this video a little bit while ago, I forgot about the negative, and I had to redo this particular video because I forgot the negative. So it's an important consideration here. Okay, now let's see what we can find out here. And by the way, this depends on other factors. This is if you jump out of the airplane belly first, like this, like you see most parachuters do. If you go head first, your terminal velocity is closer to 200 miles per hour, but it's around 180 feet per second, or 122 miles per hour approximately, if you go belly up. So let's just use that particular one. And I want to know what happens after 10 seconds, and also the other question was how soon before you hit the ground, and how fast are you going when you splat on the ground. So, okay, we'll work that out. Now then, first thing we do is from the terminal velocity, we can figure out what k is by using this relationship here. So if we solve for k is what? Is g over terminal velocity. And gravitational acceleration is minus 32, because it also is downwards, over negative 180. The negatives do cancel, so k would be, that reduces to 8/45. 8/45. So I'm going to replace the k's up there, and velocity is 180. I'm also replacing terminal velocity, minus 180 in fact, parentheses 1 minus e to the negative 8/45 t. And then altitude is minus 180, parentheses t, plus, when we divide by 8/45 here, divide by k, it's same as inverting, multiplying, so it's going to be 45/8, 45 e to the minus 8/45 t over 8 plus c. So it's getting a little cluttered, and boy, it's really going to get cluttered for the next model. But let's find out what c is. And now we have the velocity function figured out. It's done. We can tell how fast we're going after any amount of time. But we don't have position quite figured out because we haven't figured out what constant c is, and we'll get that from the initial height. So I'm going to plug in 0 for t, and we get minus 180, parentheses 0 plus 1 times 45/8, so that's 0 plus 45/8 plus c is equal to 10,000. And let's see here. If I multiply 180 times 45/8, 80 times 45 divided by 8 is 1,012.5. Actually, it's negative 1,012.5. So if I add this negative number, if I add to cancel it over to the right side, c will end up being 11,012.5. All right. So I'm going to do some erasing and write these functions neatly at the top before we go on and finish the problem. Well, let's see what happens after 10 seconds. So the velocity after 10 seconds, if I plug that in, it's minus 180, parentheses 1 minus e to the 10 times negative 8/45. That's minus 80/45. And let's see what that is. So let's see, 1 minus e raised to the negative 80 divided by 45. Then multiply by negative 180 is about negative 149.6. So that just means the negative, again, just means it's going down, falling. So the velocity is close to 150 feet per second. Now, after 10 seconds in the other model to a vacuum, it was much higher, wasn't it? It was about 320 feet per second. So the atmosphere has slowed us down considerably here, cushioned us, which means we're probably getting kind of close to terminal velocity, which was 180 feet per second. So we're, after 10 seconds, we are at 83% of terminal velocity. Okay. In case you're wondering. All right, now altitude, y at 10 will be, let's see, minus 180 parentheses 10 plus 45 to the minus 80/45 divided by 8 plus 11,012.5 is roughly, it's a bit of a more complicated calculation. Let's see, 10 plus 45 divided by 8 times e to the parentheses negative 80 divided by 45, okay, is a number times negative 180, then add 11,012.5, and I get 9,041.4 feet. 9,041.4. So let's write out those results here. The velocity after 10 seconds is about 149.6 feet per second. I didn't put the negative in there because we understand it's going down. And altitude is about 9,041.4 feet. So there we go. I'm going to, before we figure out the other problem, and by the way, we were at 8,400 feet in the other model, weren't we? So we've slowed down quite a bit falling through the atmosphere with this model. And I'll be interested to compare this to our third model, which is we're falling proportional to the air resistance is proportional to square velocity. It'd be interesting to see how that changes this model. Okay, well, I'm going to do some erasing here, and then we'll figure out the other question. How long before you hit the ground, and how fast are you going when you hit the ground? So the other question is, how long before you hit the ground, how fast are you going? Well, to solve that, I need the position to be 0. So I'm going to set this equation equal to 0, and I'm going to bring this to the left side as a negative, divide by negative 180. I end up with t plus 45e to the minus 8/45 t over 8 equals to, and the two negatives will cancel, so I have 11,012.5 divided by 180. Now to solve that problem, this is not an equation that lends itself to an algebraic answer. I don't know if I could solve that algebraically. I probably couldn't. So we could set this equal to 0 by subtracting this term. So I'm going to just make this a minus sign, make it equal to 0. And we could, again, we talked about this before, we could consider this a function and use Newton's method to approximate the roots of this function. Or we could use modern technology and just plug it in our calculator and try to figure out where does it cross the t-axis or x-axis. So that's what I'm going to do, and so I'm going to pause for a minute and figure out the result here. You should try this also. So I plugged this function into my graphing calculator, and using x instead of t, and I graphed it, and after some effort I zoomed in and found out that the free fall from 10,000 feet before he hits the ground is about 61.2 seconds. And so I got as close as I could within reason, and I plugged that in to the velocity, and the velocity was just about 180. So actually negative 180. So what happened here? It took about 61 seconds to fall 10,000 feet. And if you take 10,000 and divide by this number, it's around 163.5 feet per second. Now, terminal velocity is 180 feet per second, so the average velocity was 163. Makes sense because he does start off slower and gradually, eventually punches past the average 163.5 on his way to 180. Does that make sense? So to me, the average, this is a very reasonable answer. The average velocity was 163.5 feet per second. But after all this time, by the time he hits the ground, he's just about reached terminal velocity of 180. For all practical purposes, he's been doing terminal velocity there. So let's see. He hits the ground after 61.2 seconds, going 180 feet per second. There we go. So now in the non-atmospheric problem, he hit the ground after 25 seconds, and I forgot how fast he was going. 800 feet per second. He was really motoring. So anyway, this is a much more realistic example, and like I said, I don't know exactly what the model is. Is it first power to velocity or second power velocity, or is it in between? Believed to be in between. But anyway, so let's move on from here.